Let me introduce myself. My name is Norm. I'm an active member of the LabVIEW community for the past greater part of 25 years at this point, which is kind of funny to say. This is probably my 19th NI Connect NI week, and I love to present, I love to share, and I want to be the next Jeff Kodosky. Who doesn't know who Jeff Kodosky is? One, he's the person who created LabVIEW. LabVIEW was his idea. He saw a problem. The world didn't ask, did the world ask for LabVIEW? No, the world was doing its thing. And he had an idea and he had a vision because he saw a problem. And I see a problem, and I see it everywhere. And we're gonna get into it, we're gonna have a conversation today. And it's gonna take some twists and turns, and if you're like, this is not what I expected, because I expected that, you will not hurt my feelings, because there's about 4 other really good presentations. I'm really surprised I have this many people in the room right now, so don't worry, you won't hurt my feelings. But I'd like for this will be an interactive conversation or a very short presentation, one of the two. So, it's not about pizza. Did I do the thing? Come on. Worky. There we go. We're gonna talk about automated test. We're gonna talk about automated test in a very interesting way. Because I wanted to have a conversation to lead that bigger picture of this future that I think needs to exist, the tool that the world is not asking for, that hopefully by the end of this conversation that we're about to have, everybody goes like, when can you make that? To be really, really clear, I work in the aerospace defense and government business unit. I do radar and EW systems. I'm a kind of a market segment manager, if you will. But LabVIEW was my very first passion, and automated test followed very quickly afterwards. So, fact 1. Well, most companies, I could probably put all, but I put most companies here perform automated test. Does anybody here not do automated test at their company? Right. Hypothesis 1 is proven true. But it's an incomplete statement. Most companies do automated tests poorly. We're gonna talk about that and how to make that better. Fact 2, this slide deck has four slides, and you've seen them all. So, at that point in time, we're gonna pivot away from slide decks, which you've probably seen plenty of, and we're gonna have hopefully a little bit of an interactive conversation. So as you see things, as you agree or disagree, challenge these hypotheses that talk about automated test. Because the idea of executing automated tests starts from typically a plan. So who here remembers COVID? Groans, right? Yes, exactly. So during COVID times, I'm actually gonna go ahead and pivot this so I don't have to look at 2 monitors, so please forgive the glitch while this does its thing. There we go. And during those times, there was a company in town that was developing something to help with ventilators. Right? This is a company called Sisu. Does anybody here work at Sisu? They're one of our partners and stuff like that. They do great work. But they pivoted from what they normally do, and they're like, we're gonna make something to help people who need to breathe, right? And it's basically so somebody didn't have to stand there and squeeze that bolus all day long, right? And it was just an automated bolus squeezer. I think it's a bolus. Somebody know what that's called again? Anyways, the big plastic rubber ball that goes in and out and helps somebody breathe. Well, they decided, and I was like, hey, we want to help whoever's doing stuff however we can. How can we help? And so they're like, we need to develop tests. We need to do automated tests of this thing. And we have people, but if you can help us do that faster, great. And I'm like, me, please. I love automated test, right? Remember, that's one of those fact 0. I love automated test. So looks like a very simple device. It has a couple knobs and a couple buttons and a small display and some motors that actuate. And so the plan was on how to do this, if I can find the right, here we go. Here is an automated testing manual. We'll get zoomed in there tight. Right, there's some of the guides, but if I back out here, this is an early release of it. Hey, this right here is the encoder test. Actually, I guess I gotta make it bigger just for actually let's do this. I can make this easier for everybody. There we go. So basically, a small, long, linear list of the plan of how somebody's going to execute this singular test in the system. And there was multiple things. There was a pressure sensor in there. There was a firmware burn, a button push. There's a bunch of these that I can show. We don't necessarily need to do it. Who here automatically can understand, like tactily, what's happening by reading this, right? some people are reading it like, okay. And what's happening in your mind? What are you doing in your mind reading through this plan? You're assembling a picture, right? Why did LabVIEW get created? Somebody had a vision of a picture on a napkin, and that should turn into code. And that's what I want to program to. I want to program the vision that I have in my head on a diagram. I don't want to read through text of a code. I want to see a picture. And it should describe something. It should describe what's happening. When is it happening? Well, let me just cut right to the chase on this one and show you what this turned out to be. Where's the encoder test? Production test, LCD test. Let me see if I can find that same encoder test. There we go. If I scroll slowly here, how about now? How many things are involved in that specific test? Anybody want to take a stab? I'll give you a hint. I'll wait for you. Somebody said say it. Three, thank you very much. Exactly. Right? Last session of the day, right? This is how we stay awake, folks. Indeed, there's 3 things involved. Very clearly, we know what those 3 things are, right? This is the model that you're building in your head. An operator, I have an optional ready, one, the test system needs to get to there. How about now, aside from the fact that I wish I could lock that top screen, right? We just have to remember DUT's on the right, person's on the left, code in the middle, right? Right? Well, the code's gonna tell the device to start the encoder test. And then it's gonna prompt, hey, go ahead and turn all knobs to 24, rotate the knobs clockwise, so on and so on and so forth. Until we get to the end of it, there's a loop, rotate knobs, get this back, and eventually observe success, ideally, right? This is the happy path, right? How about, we kind of went through it and I didn't read everything. I'm sure you don't want me to do that. We want to stay awake, remember? But you kind of get an idea of what happens when and what step is interacting with other things, right? Hopefully is this not an intuitive kind of view for to describe the interaction of multiple independent asynchronously running things in a system, right? This is exactly it. This is the vision that I was building in my head. And you know what? I accidentally stumbled upon this idea because I got their test plan and I'm like, I'm so ADD. I have such a hard time. I cannot keep 2 things spinning in my head at once. So I just started documenting and drawing it down, and I stumbled across, this is called a sequence diagram. It was created from a tool called sequencediagram.org, which you saw originally talking about the pizza cooking. Do I not have it up? Hold on a second. There we go, right? This is a conversation of hopefully a future and a vision that's gonna start with you recognizing that when we do automated tests and we do it poorly, it's because we're not starting out by thinking about it in this fashion. And ideally, we're gonna lead to a conclusion that is also how you actually get multiple things not only visualized, but talking to each other instead of you doing all of the commanding. Because what ends up happening is if you create your test program visually like this, you will find out things about your program. Basically, you will mentally and visually compile what's gonna happen by looking at the interaction of different things, and things will be revealed to you. And that's the basic idea. All right, questions so far? Once again, there's no more slides, and I'm not prepared. So that's actually kind of funny, right? This is a presentation about doing planning, right? So I was very out of sequence for getting ready for this. Questions, thoughts? So Mark, an esteemed member of the LabVIEW community is up here. Have you ever gone through the process of taking a test plan and putting it into a sequence diagram?
No.
No. Has anybody done that before? Am I the only weird person in the room? Yes, I have friends, finally. Okay. So yeah, I saw some heads nodding. So that means that you must have seen. Did you see that what kind of things did you see? What was your name, by the way?
Me?
Yes, ma'am.
Sandy Barker.
Sandy, hi, Sandy. So when you were doing that, what kind of things jumped out at you about the ordering and the planning of what you were doing that maybe worked or weren't going to work? Or was there anything?
So, actually, it was my students that were doing it. What worked and
not going to work.
Did anything get revealed by virtue of having it in that format?
Oh, sure. Yeah, you find missing steps. You find things that are not going to work logistically.
Yep.
Yeah. Off the top of my head, I can't.
No, that's
Those
great.
are like the big things. Yeah.
That's fine. One of the things that I saw while doing the encoder testing, actually, even as I was showing it to you, right? None of us can stop engineering when we kind of get on a tear, right? And one of the things that jumped out to me, if I can find that automated test here, can anybody find a bug in this code right here? Has anybody ever used the magic delay fairy in their code? Do you know what does anybody not know what the magic delay fairy is? Has anybody ever put 150 millisecond wait between two function calls just to get the thing to work? Yes, and it's waves of nodding heads and embarrassment flows across the room. Yes, we should all feel guilty to some degree, but to some degree that's needed. Now we can talk about how to do that well. How about Sir Loops a lot? Does anybody know about Sir Loops a lot? Just keep doing it until it finally clicks, right? How about Max the retry guy? Anybody know about Max, right? Just do it at least 5 times. If one of those passes, it must be okay, right? The reason that most of those things, the bugs, the things that jump out at you, is because you're missing some critical information, a visualization, a realization about the interaction of the multiple things in your system that, because we have a limited degree of creativity in our head to hold all that information in there all at once to try to do that job. I can't do that. This helps me. I think the world needs something like this. I mean, see, this is an image. Does the world need an image? No. Does the world need a tool to make sequence diagrams? There's already tools, right? The website that I had up that was the pizza. It's a great tool. We can talk about that a little bit more. But I believe what we need and what NI needs, because I want NI to make it because it's my vision and I have no authority, is the idea that we need something that actually, like a block diagram as a picture, becomes the code. Becomes a higher level diagram that can actually show the relationship of multiple things working together. Well, and anybody in the audience that's thinking, isn't that what DQMH and Lumos did? We'll get to that in a little bit. But one of the things that's very clearly, hopefully, hey, red dot, perfect. I say start in, I didn't say that. Whoa. All right, the bug. One of the things I say about DUT control, commanding the thing under test. 80% of the time, it's 100% a pain in the right? Somebody put commands in firmware on a device to work. They normally didn't do that to test it. And usually testing is a pain because of it. And there's my problem right there. I said, say, start encoder test. And then I told the operator, rotate knobs counterclockwise. Actually, first thing, this is the beautiful part of it, I realized I needed to have that to tell the user, okay, cool. Well, now my program is prompting the user, go ahead and do this. And then all of a sudden the operator starts rotating the knobs. I didn't get feedback from the device to let me know programmatically it's ready to go. In comes the magic delay fairy, right? Why do we need to put the magic delay fairy in our code? Because the thing's not ready to respond to whatever we just asked it to do. Who here does Skippy commands, right? Over Visa, right? That's very frequently. The reason that the magic delay fairy exists because GPIB and Skippy commands were birthed from button pushes. Hey, the easy way, the dumb way to do automation is let's just reproduce every button push. And who's gonna button push something faster than once every 10 milliseconds, right? So they never tested it to run fast, which is why traditional instrumentation, not NI stuff that wasn't made for automation, has problems and why it needs to have those delays in it, because they didn't think of automation at speed. Well, problems like this, if I start to rotate the knobs before it's ready, I don't have any feedback, in comes a bug, right? So maybe I'll do this and before I prompt to the user, I'll just wait some time before I prompt the user. Or I can ask the person doing the firmware, let me go ahead and send some information back to the actual calling system. That's the difference. A diagram like this helps illustrate breakdown in feedback. Because if you could take this diagram and basically compress it, compile it vertically, time is the vertical axis here. Hopefully everybody kind of got onto that one at this point, right? If you could compress it, all of a sudden you would find out, oh my gosh, nothing is stopping me from rotating the knobs. Well, in this case, let's say before prompt was there, I could start rotating beforehand or afterwards, right? There's a relationship between all of the parts and pieces that's not really clear here, but I've got a different one that I can actually throw in, presuming it doesn't jump around. Let's do uncoordinated RF plus. Let's do this. I'm gonna open the tool, go to sequencediagram.org. Gonna delete that program, put this over here, perfect. So this, let's see, can I get, we're gonna do this, hold on. Export to PNG image, there we go. Perfect, mostly. So this is a relationship between some RF things and DC power. I call it RF plus, right? But, oh, hitting the laser presses F5. That is unexpected. No wonder that was reloading. Okay, no more laser. I guess I will just do the virtual laser. There we go. So multiple different things, devices under test. Each one of these things are different, different parts in an instrumentation system, right? Can anybody see what could possibly go wrong in this system? What would happen if I compiled this? I don't even need this anymore, do I? I have no more slides. What would happen if I compiled or compressed vertically this diagram? What might happen before it should? You want to take a stab at it? Just think about every arrow that's going left and right and forget the fact that it's locked in that position. Each one of those rows is an asynchronously running thing. There is a person, there's an instrument, there's another instrument. Don't forget, every instrument has its own engine in the guts of it. Whether it's PXI or GPIB or whatever, there's some firmware constantly running on that. There's a state model behind that instrument. There's a state model behind you as a person, right? You're getting input, feedback, you're moving between your modes. There's this thing that's under test, also in some cases has that. Anybody want to take a stab at what could go wrong here?
You don't know if the DUT's powered on.
Exactly. You don't know if the DUT has done anything. Actually, even start acquisition, the way it's sequenced is start acquisition does start after generation, but is the DUT ready to actually have the signal? Has the generator even started generating, right? Nothing is instantaneous, right? MI drivers clearly clean the clock of almost any other instrument vendor out there. I could swear it up and down, let's do a drag race. But when it comes down to, you're still responsible for doing good automation because nothing happens instantly. So the best way to make sure that you have a stable program is to be able to facilitate feedback when it's available. Now, not everything out in the world has feedback, I'm ready to go. And that's okay. That's why the Magic Delay Fairy probably still needs to exist, right? At some point in time, if you don't have feedback, you just have to be smart about it. But it's not a guessing game. It shouldn't be a guessing game when it doesn't have to be a guessing game, right? We make test programs, our test programs fail. Right? Let's just average until if the more I average, the better it gets, right? Let me show you exactly why that happens because that acquisition can maybe start too soon. So if I do, I think I can do this, Control-6, If I had an average and I said, hey, what is my average value versus time, right? And what if the resolved average value over time did one of these numbers? What would you presume? Two people, come on. What would you presume? This is average, this is number of averages, so time. The more I average, the value comes down. What would you presume about that signal?
It's noisy.
It's noisy. And if you want a clean signal, you better average for a really long dang time, right? Of course. The more I average, the more better. Great, let's pass our devices. Except, I'm gonna show you the actual value of the signal versus time, because you presume It's a signal that maybe looks like something like the actual signal, maybe is noisy or something like that. And the more we average, right, go with not drawn to scale here, right? But what about if the actual performance, the actual output of your device was boop? You would end up with the exact same curve. Ooh, I'm really driving it here, sorry about that. You would end up with the exact same curve. Did you need it, in Costa, a colleague of mine, asked, right, is it time in the bottom axis? And absolutely, the more you average, inherently, you have no choice but to take more time, or you have more inputs. I guess you have a conversation about that. But in all but rare circumstances, to do more averages, you need to take more time to do the job. So if blue is the true signal that happens, what should we do? Anybody want to take a stab at that one? Should we average to get the result down? Kevin?
Trim it.
Trim it.
Right after that transition.
Trim it right after that transition. Absolutely. Or just delay when you start taking data. Or wait until you get a signal from the thing outputting this, it's ready to actually go. Then at that point in time, your test time, what happens to your test time by doing the planning like this? And your test time goes from, hey, I wanted to reach that level right there. So instead of doing, oh God, nope, that was bad. Right? Instead of going that amount of time, I merely delay that amount. And now I can just go ahead and basically take, one record, if you want to call that one record of the blue line right there. I'm already underneath. But you don't think about it like this for bad reasons. Right? You're not thinking about it like this because maybe the thing that you're using doesn't give you the ability to get insights in terms of how is it performing in the time domain. You're also under a crunch, and what's the thing that made it work? Average more, right? That's just what you have to do. But the thing that I will say, the hypothesis that I'd like everybody to walk out of the room and go, hell yeah, is that if I had more information coming from either my DUT or coming back from I think that's RF out enabled, and then we waited, basically we needed something to wait in the program for some feedback from something else. Now that is called software-driven coordination. Let's get back on here. Right? Or we can take it one step further. And instead, once you have the simple flow of the program is saying what to do and when, you send the instructions to each one of the pieces of the system. DC power on. When DC power goes on, it has an exported signal that goes to, indeed, the DUT. Sorry, that's power enabled, actually, to the power going to it. But there's event source complete. That goes to RFSG and RFSA. Cool. Now my analyzer and generator know they were just waiting for that signal. Cool. The DC power has said it's time to go. Then the generator starts generating. Well, one of the features of our generators is generate and export an event at a very specific sample of the signal that you're generating. And guess who's waiting for that? The analysis routine. And at that point in time, we know exactly the power's there. The signal generation is there, and everything's happening, and we've basically maximized the test time because we've compressed that down, not by accident, but by deliberate leveraging of things that are in the system. You need to know your instrumentation in order to create a good plan so that you can actually start to stitch things together, not by accidentally working, but by deliberate design of the plan. Once again, you need to know your instrumentation better. Once again, everybody automated tests, nobody left their hands down, so we're automating things. Do you know your instrument's capabilities? Or do you even have an instrument that has good enough capabilities to automate? Once again, this is what I believe down to my, soup to nuts as it were, right? When it comes down to it, NI stuff was made to automate. I love LabVIEW. I love PXI stuff. I know there's other instrumentation. Totally okay. This is not a sales pitch for what we do, but dang it all, we got a lot of features on our things and they work well. So this is something that you hit one button. What becomes of your test program? I have a bunch of setup calls and one initiate. And then the program's basically waiting. You see fetch record, right? Initiate and fetch record. And of course, it's gonna have a timeout on it, but it just sits there waiting for that result to come back. It does nothing else with the instrumentation, as opposed to what we were looking at before, where it was very clear where it was software coordination. Once again, hopefully the sequence diagram helped elevate that to your face, where you could see the interaction of multiple pieces of asynchronously running stuff. In these cases, it's instrumentation, a device under test, and a person. Now, if we were to take this concept, so I'm gonna pause. One, I need water. Two, let's hear some feedback. Thoughts? What kind of tools do you leverage about the things that are part of your sequence diagram? Does the sequence diagram help elevate any of those things that help connect those dots?
What you've already pointed out, the biggest thing is order of operations mistakes that you would make if you were just straight coding without drawing it out.
Perfect, thank you. Anybody else, any other thoughts? Who's gone from like, I don't get this to, ooh, this is pretty interesting? Oh man, okay, I think it's just we need to change topics. I play harmonica, I used to play, I know how to play kayak polo. We can totally change topics. What do y'all want to talk about instead? Because really, I mean, who runs into problems with automation that you find out after the fact that it's due to order of operations or you didn't sequence things right? Yeah, come on, I do all the time. I was doing it, trying to get ready for my demo downstairs on the floor. I was trying to control a beamformer and a generator and a DC power supply, and sure enough, everything was going sideways. Things weren't turning on when they were supposed to, and I'm like, let me just take a step back, because I didn't create this first. And then after I took my step back and I went back and I documented what I had done, then I need, okay, very clear, of course. How many times do we get into a bug and at the end of it, we're like, well, duh, right? But there's a lot of fighting the system. Even if this presentation, yes, Costa.
There is an arrow labeled dot output signal. What does that mean?
Dot output signal. The dot is outputting the signal at that point. That's just for me to illustrate, to some degree, that's my feedback, right? That's my illustration, ideally, of saying, hey, source complete, RFSG turned on, it's gonna do that. So basically it's illustrating that line all the way over to the analyzer, which is getting that dot signal. So what's your point? Yeah, what's your question?
The question is, what if the dot is rather bad and it doesn't output anything?
Oh yeah. Well, no, that's a great question. So if the dot doesn't actually output anything, there's something wrong. Indeed, that's a bug with the device. I'd say that's part of the iterative process of this, is that you put together how you believe it should work. And then from there, if it doesn't operate in the way that you think it should, then you need to start understanding its behavioral model, its behavioral state model. Remember I said, the generator has its behavioral state model. We expect that when event source complete is done, it's doing the thing. If for some reason it doesn't, then I need to reinterpret in my brain what that signal means at that point in time.
Well, okay, so the thing about the dot,
Sure.
Why are we testing it? If we know that it's perfect, we're wasting time. But if it can be broken, so broken that there is no output signal, are we doing something wrong, assuming that it'll output something all the time?
This is for character. So this was done for, maybe that's a difference. This is not just is it working test. This is characterizing its performance. So I need to test it to determine where it is in that whole other system. And so yes, there is a presumption of when I'm going to be testing, sorry about that again. If I'm going to be testing the DUT, then at that point in time, it's going to have a valid operational behavior. So, okay. So, but I think that is that twist. Why do we do these weird things with our instrumentation when we automate it? Because we don't properly understand why it does what it do. right? Visa Open. Who uses Visa Open to open up a reference thing, right? Everybody should be raising their hand here. Come on, y'all. Wait, okay. Everybody should raise your hand and just humor me. Just come on. Last session of the day. Oh, there we go. Okay, and then we go down. Perfect, okay? Right? There's an instrument out there. It was an old HP DC power supply when I was working at the TI. And you would do open reference over Visa, and you would close reference over Visa. And normally we would imagine open and close reference over Visa pretty much should leave an instrument alone. Close reference shouldn't change something over a Skippy instrument. But sure enough, it resets some register in the guts of it, right? We had no idea why. We just knew canon law, don't do close Visa session. Otherwise it'll spike your DUT, and that would be bad, right? So that's an operational behavior that is necessary to understand, because you can't plan unless you have an idea of what you're about to work with. Right? In the name of planning, what am I saying that we should be doing? One, think about the parts of the system. Get them visualized out. And then start to piece together, if somebody gives you a test spec, actually it was kind of funny with the AI thing, like here's your test specification, and the whole thing in the keynote this morning where it automatically made that, I'm like, just make a sequence diagram for me. Just have it make a sequence diagram for me, right? But really, that's what we have. I mean, everybody gets test plans, do. They're all doing all over themselves, right? And so what ends up happening is, okay, take that, turn it into this, and realize, hey, how can I do better? Or possibly, if it's first pass instructions of how to do the thing, what's wrong about it? Because really, how does somebody come up with those test plans? They manually manipulate something until they find a way to make it work, and then they start writing it down, right? But what if that, instead of doing it like that, the original person putting together the system, either this got made for them by watching IO trace, right? If you're gonna automate a system, right? Does anybody not know what IO trace is? Okay, well, okay. So IO trace is a tool that logs every instrument command going to either a PXI or over Visa on your test system. If you've never seen it, it's a fantastic debugging tool. But there's nothing that ingests the output of it. It blows my bloody mind. I really can't, I'm like, why does this not exist? Because then you wouldn't even need to go ahead and make one of these things, right? You could just run your program and you'd see basically a bunch of commands from the application out. And you could see the order of operations and how long things took just by default. That's your starting point. And then you start to draw lines and interactions for where's the question, like the signal going to the DUT, right? Okay, well, let's put a DUT in there because the DUT's really never part of that IO trace, except in rare circumstances, right? Hey, where's the signals? What's happening where? And now, going back to truth number one, most people do automated test poorly because you don't take that, frequently at least, you don't take that step back and say, okay, how can I go from that simple, hey, my program's just sending commands, to how can I leverage the feature set of my instrumentation that facilitates auto coordination, much like this, what we have here. Everybody automates. Very few people understand how to do coordinated automation in an efficient way. Most time the program is doing the coordination, and that's okay. We all automate that way. But if you start to have something like this, then you can start to, well, in the simpler view, then you can start head scratching and looking at it from afar. At least that's the way that I work. I'm a LabVIEW programmer. I like to see those things. And now I can go, okay. And that's exactly how I birthed this, right? I knew there were driver features. I didn't know how I could make them interplay. And maybe I got my program working, and then after I got it working, I'm like, okay, I need a document to describe what this is. Because a lot of people in the room here is not a LabVIEW programmer. Oh, fantastic. Okay, so there's a few people not in the room, okay? So LabVIEW inherently is graphical. Some of you might be saying, doesn't LabVIEW show you data flow and show you interaction of things? Sort of, right? Not only does LabVIEW not show every piece of the system, because there's not a U, this is application here, right? But if we go back to the original one, it wasn't application on the left, it was you. It was a person, it was the operator. An operator isn't visualized on the block diagram. Also, the other thing is, all of these operations that you're seeing here, hey, look at my shadow, right? All of those messages going back and forth, those are automatically happening because of trigger lines between the instrumentation. That's not on a diagram. And then you take it one step further. Most applications nowadays are made up of, do most people make good applications by making one monolithic function that does everything? Or are most applications made up of probably multiple discrete asynchronously running modules communicating amongst each other for functional containment? That's what's happening. DQMH, Active Framework, the two pretty much leading of the pack of frameworks within LabVIEW to develop your applications, and probably other ones in other languages too, kick off things to run in parallel. Now, the people at the DQMH consortium, if I open this up and the internet doesn't fail me now, this is the output of a tool for add-on to DQMH, where you can run your program made up of a bunch of asynchronously running things, and they're flying messages back and forth between each other. And now you can see what happened when. And guess what happens when you're trying to debug? What are you trying to find out? What happened when? Why am I dealing with my bug? Right? We spend so much time debugging our code, and it's usually because of interaction between multiple asynchronously running things, be it your device, your instrumentation, the operator, the internet, whatever. The sequence diagram is the language for describing over time interaction between multiple different things. You can take advantage of it. Try it. It's free. I'm not selling a dang thing up here. We don't even make a product that necessarily does this part. Well, DQMH does, I guess, at this point. But still, this is just illustrating parts running in a system. This is not actually describing what's the operator doing, what's the device under test doing, right? There's still more information. This is not even fully describing. But as a minimum, you take something that you hit a run button and a program does its thing, right? This can reveal what it's doing. Indeed, during the thing that you couldn't see up on the screen was basically an active log of it being created real time. It's actually pretty cool. This is basically that thing turned into an image after the fact. And at that point in time, you should be able to take your step back and say, why did this thing not work? And you start to piece it together. And maybe you start adding more information to a graphic like this, or you start drawing it on a piece of paper. Okay, this message happened here. What was the internet doing at this point? Or what was the network connection to this other thing over here doing, right? This is the opportunity to reveal that. So for the sake of time, the filtering by time and filtering by event, because basically if you're recording everything happening in a system, there's a lot of stuff happening, right? And so this actual tool, once again, I'm not getting paid for it, I'm not sponsored by them, but this is actually pretty cool because then you can say, hey, get me this 8,000 line thing of all things that happened in the system, take me to this time epic, and let's look at what happened around that. Really, really nice feature. The reason that I find it so relevant and compelling is not only because of what it reveals, what it actually shows you. It is difficult to plan like this up front, but there's anybody here do model-based systems engineering? Right, okay. That's the whole thing, and the sequence diagrams are absolutely part of this. Let's create a bunch of sysml and other kind of markup language documents like this to describe what happens when, but usually that's not a measurement, right? Model-based systems engineering is like the system. But the essence of what they're doing applies to us as test engineers, doing a discrete, singular measurement. What I like to say is this is one strategy of how to do things, right? This is a test strategy. This measurement gives me the exact same result as the other one that I had up on the screen a moment ago. Same inputs, two different test strategies. And that's really the way that's why it's like, basically plan and strategies and test. These are the things that you should be thinking in your head. That's maybe what drew you into this presentation in the first place. This is a way of basically visualizing and creating basically the plan of what's happening when. Now, here's the vision casting into the future. Here's why I want to be the next Jeff Kodowski. Because the world isn't asking for something that allows this to code gen. The world isn't asking for something that says, make sure that this stays aligned with my code, because what about when I rearrange my code and I make it do different things? What happens to the system? You have to recreate this every time that you modify the code. That inherently is a problem, right? I want that to exist. I want the creation of what happens on a diagram to be, hey, you do it to, who does a measurement that has multiple things happening in it? More than one instrument? Anybody? Okay, perfect, right? How nice would that be to just be like functionally like, all right, how should this sequence run, right? Well, let's just put my things up on the chalkboard and let's take a piece of string or wire and connect. Success, right? Result on the bottom. Why can't we have something like that? Why can't that exist? It can. I don't know how easy it is to make it, but the world isn't asking for it because people aren't thinking about that they do automated test poorly. They think, I'm doing my automated test and it's great. Guess what? You could probably be doing it better, but it's hard to know how you can make it better because you're not either taking advantage of the instrument that you don't know all the features of, or you don't know the relationship of the things happening in the system and you're just barely making it work. So if you were to have a tool that actually allowed you to very quickly sequence multiple things happening, it actually gave you the ability to, actually this tool is actually pretty slick because not only is it text-based, I can click on like a line and it takes me like there. So this just as a tool is cool. This is not an NI tool, it's free, it's online. But I can select an individual thing, it takes me to that part of the code over there. But I could also right-click and do very specific extra things in the code right there, right? What about if I was right-clicking on RFSG, it told me the commands I could do at that point. It gave me the ability to discover the feature set of the driver that I can use to do hardware trigger, export event. And instead of looking through a reference document in a help file, you're interactively discovering the features of what's available and you're putting together that interaction and you hit go. And it could either run or code gen the base level functionality for you to possibly extend after that point in time. What do you think about that? It doesn't exist. The world's not asking for it. I can jump up and down in front of Ritu and say, we should make this thing. And she's like, great, who's gonna buy it? I don't know. And if I'm still failing in this room right now, I should probably just give up. But if you're getting it, if you're getting the idea, you're like, man, yeah, that would be kind of nice to just do this instead of a Python script, or instead of a DQMH module and do a queued message handler, or instead of just doing railroad tracks on a really, 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 really long LabVIEW VI, right? What would that be? Would that accelerate your life? Would you buy it? I mean, that's really the question, right? I mean, I'm kind of looking for excuses to go back to leadership and say, I had a whole room full of people going, this would really change the way that I design and develop tests. Whether you're doing something RF or water valves or meters or electricity, just whatever you're doing, right? You have your thing that you're testing, you're interacting with it, you have an operator, you have yourself, you have an engineer, whatever. How nice would that be if you could make your sequence of things graphically? Not just the code. A programming language is a sequencer with poor sequencing abilities. A sequencer is a programming language with poor programming abilities. That's how I think about test stand and LabVIEW, right? They have their strong points and they have their weak points. What about if this was a level above that? What if there was something, maybe an Instrument Studio Pro, that allowed you to do this to describe what should be happening between, like they were showing the sequencer in this morning in the keynote, right? Hey, drop a couple steps and you do a loop. Great, but it still reads out the exact thing that Jeff Kodosky didn't want. Linear, sequential, non-descriptive text. It's easy to understand. We can all read books by now, hopefully, right? That's how we read, top to bottom, left to right. Let's do those things by text. I'm not a text programmer. It takes me at least a good 48 hours of bitching and moaning when I have to start debugging somebody else's source code in text before I finally give in and I'm like, okay, I can navigate this because I'm a LabVIEW programmer, right? But for anybody else who's in the room with me that also struggles with that, or even other languages, once again, if you're using a different language, you want to use something NI, how are we helping you? We give you examples, regardless of language, to try to figure out how to do this. Wouldn't it be easier to start here? Output to LabVIEW, output to Python, output to C#.NET, Rust. Anybody a Rust programmer? Anyways, right? Wouldn't that be an interesting thing? Anybody? No, seriously. I got one thank you. I got one nod out of the room. You and me, we're taking this castle by storm, right? But that's the reality. But if you're not sure if it's valuable, toy with it. Take one measurement. I dare you. Take one singular measurement that you do right now. You don't have to change your whole test program. Go to sequence. I'll zoom in up there for y'all. Red. Y'all can see that? Yeah, sequencediagram.org. It is the only tool that I've seen where you get real live updates. You can change the text and you see the update over there. You change the thing over there, it updates the text real time. And it even tells you like when there's an error. So there's a little bit of, debugging and stuff like that. And the reason this one's so important to see the text, because there's like Lucidchart, who are some of the, there's a variety of drawing tools, Visio, right? They exist, but there's nothing that keeps that relationship clean and crisp. And sometimes the tools that try to be really smart from like model-based systems engineering, if you move a wire, everything rearranges on you by accident, right? There's a WYSIWYG tools where you can click and drag and drop, and then everything goes crazy if you do the wrong thing. And then there's text-only ones, but you don't get the real live feedback back and forth. So I've researched, I found, if you know a better one, let me know. This one I keep going back to and I can't avoid it. It's beautiful, it's wonderful. But of course, it doesn't make the code for you, right? It doesn't stay aligned with the code for you as you change something. But as a minimum, it's getting you there. So take one of your tests. Turn it into a different kind of plan, right? Create the visual, the graphical plan for the strategy of an individual measurement you're going to be doing that has multiple things happening in it. Maybe, and put it in front of somebody else. Ask, here's the real test. Take your code and say, here's my block diagram, or here's my pie file, and then here's this. Person trying to ingest my code. Tell me, you get 5 minutes to take two, there you go, two people that you think are equal. Give one person your code, another person the diagram, say, you got 5 minutes to figure out what happens in my code. Go. All right? And see who comes out ahead. Because guess what happens? Would you, by a show of hands, let's just do this once again, end of day. Who would like to inherit somebody's code that had something like this? Right? The world needs something. Yes, Mark.
So this is you're just mapping out the happy path, right?
Yes, thank you.
So every time I get a branch or an if-then statement, I got to create another sequence diagram?
Yes. Thank you. You are thinking about this. That is 100% part of the reason why this is a harder problem and why some head scratching, this is why it doesn't exist in the world. Because yes, to fully describe a program, this is not able to fully describe a program. It can. So a little history lesson. Once upon a time, does anybody not know what the for loop in LabVIEW looks like? I know there's some text-based programs in here. Okay. Once upon a time, that was a confusing thing. That didn't exist. People sat down, they're like, how can we graphically represent a for loop on a diagram? And they were confused about it. Us LabVIEW programmers take that for granted. Looks like a page, it has an N, has an I, and has a little N, right? Now it's got conditional, right? But they didn't know. It took an aha moment to go, if I do it this way, I can make a case structure and it can have multiple frames and I can put a thing up top and we can put multiple code in a bounded box on a block diagram. We can do a case structure. That's the graphical representation. So in the name of this, definitely, as it shows, is only describing the happy path. Absolutely. What happens when something goes wrong? Yes, my short answer is this is a description, much like the test plan. Right? The test plan doesn't say what to do in every condition, does it, right? This is a one-to-one map of the test plan, and then you can have a different plan for when things go wrong. Now the twist is you have multiple plans, how do those turn into a single piece of code, right? That's kind of where it breaks down in terms of keeping it mated and aligned with the code so that you don't have to keep going back and forth and doing this. But I think that's part of the engineering effort. Just like Jeff Godowski trying to figure out how to draw, what is a for loop on a two-dimensional canvas, right? What is that? Just like that, I think we need to go down the path, because if there's enough people that say, yes, oh man, champagne flows from the ceiling, velvet ropes open up, peace and serenity. I mean, that's really, when I sequence diagrams, when I first saw this, I had somebody accidentally, there's a CLA summit, it might have been Kevin over there, I don't remember who it was, but I saw it, I'm like, everything makes sense. I can describe graphically what's happening in my head when I'm describing multiple things in a system all doing their deal. Be it multiple pieces of software, an instrument and an FPGA and a C-RIO out there, whatever it is. Because I hate reading. That's why I do LabVIEW, right? Reading puts me to sleep and it makes me cranky. I'd rather draw. It's okay to still have fun. Anybody remember that banner? Used to be one of the ads from LabVIEW years and years ago. It's okay to have fun. It's just a picture of somebody, scribbling LabVIEW on a wall. That's the same thing. Right? I think this can revolutionize test. I think this concept is around. People know what a sequence diagram is, but I think it needs the next evolution. It needs that next evolution so that you can describe the strategy for how you're performing your thing, if not for you, but the person who has to get your code after you. And they have to spend days and nights and weekends ingesting it, trying to figure out why and how this thing is supposed to work, because you got it functional and maybe never went back and created that. Or maybe they're just not, they can't hold all of the pieces in their head all at once, right? Do that for that next person, right? It could be you. It's probably you, right? That's usually what ends up happening, right? Years down the road, how does this thing actually work? And I can tell you this right here is a very simple program with some very complex interactions. And so the code definitely no longer really describes what's supposed to happen when. Because look, I'm setting all my initiate and wait for trigger to RFSG. It's actually commit. Let's see, I could probably change it. Let me just go. Let's just do, there you go. Configure all fancy triggers. Control Enter, there we go. Ooh, there we go. And then I'm gonna go to RFSA, configure all fancy triggers. Control Enter. And then I think I should be able to do, there's that there. I think I can do parallel. And then do off. Is it parallel off? Parallel off. There you go. So in one fell swoop, in parallel, I'm configuring all the fancy triggers. So my code basically has 3 major steps. Configure fancy trigger, initiate and wait, done. Right? So the code, that for anybody who's like, yeah, doesn't LabVIEW graphically describe what's going on? No, it doesn't. Just like Python doesn't, just like Rust doesn't, just like whatever doesn't. Especially when you're doing automated test well. Once again, this gives the exact same output as the other example that I opened up earlier, but it does it better. It does it without error. It does it stably. And if I need to add some weight in there, I can characterize it because I can actually get to the moment in time and I got a trigger, wait 5 milliseconds after that trigger. Not a magic delay of, 100 milliseconds works, right? You can get to that and you can adjust things so you get it right on every time. You get the same timing, so you get more stable results. Once again, this is test strategies. This is creating a graphical way of visualizing your test strategy for the purpose of the next person, who could be you. Also for your own benefit to figure out where bugs may or may not exist, and then if done well, also reveal how can I do it better. But we need this to exist. And I need help making a case or saying, hey, I heard about this sequence diagram thing. Can you add that to Instrument Studio, right? Take a crack at it, right? Make an early access program. I don't know what features need to exist, but I appreciate that everybody raised their hands like, I would like to see this. Is this something that you think would be good in Instrument Studio to showcase multiple things happening at the same time? Okay. Would you buy it? I guess if it was I mean, once again, I don't get money from this. I just work here, right? Is it the kind of thing that you would say, yeah, that's a value add? There's a value add to my system. It's going to help somebody else. It's going to help me. I'm going to get operational faster. I'm going to discover features of my instrumentation more. Would it be something that's worthwhile to even purchase? I got at least a couple nods. So that's, once again, if I keep the cost low enough, 2 people will be happier. So, all right. So with that, I'm going to go ahead and say thank you. Anybody have some burning thoughts? I would love to have some. Kenny, how are we doing?
Good.
Are you ready to charge up the hill with me?
Yeah.
All right, I will take that. Trust me, Kenny, I won't lead you astray. All right, everybody, with that, y'all have a great rest of the day, and thank you for coming in iConnect.